everyone. In this video I will discuss the underestimation of band gaps in density functional theory simulations and how to obtain an accurate electronic band structures using the Hubbard correction, or the so-called the DFT+U approach. First, I will give a brief idea on how the DFT simulations work. Then I will address the question of why DFT simulations underestimates band gaps and what's the Hubbard correction. Finally, I will present some of the practical applications showing the modeling of electron transfer and optical properties using the Hubbard correction. The DFT approach tries to circumvent the difficulty of solving the many-body Schrödinger's equation by expressing the problem in terms of electron density. This facilitates mapping the problem of n interacting particles, which has 3 n variables, to a much simpler problem of non-interacting particles where the charge density has only 3 spatial variables. This implies that these non-interacting concham electrons would live under an external potential such that their density is the same as the fully interacting density. However, since we do not know what's the electron density or the charge density should be, we begin with an initial guess and try to solve the problem self-consistently. In a more detail, we calculate the effective potential, which depends on the external potential as well as the exchange correlation term, which takes the many-body effects into account, then solve the concham equations in order to find the eigenwave functions. After that, we calculate the electron density, since the probability of finding an electron in a certain region of space is basically determined by the squared magnitude of its wave function. Now we can compare the obtained electron density and with our initial guess and hope they are the same. If not, we reiterate the solution again till the convergence is achieved. This is what a self-consistent solution implies. In this process of self-consistent calculations, we basically monitor the convergence or the solution convergence with respect to the so-called energy cutoff and k-point sampling. The energy cutoff refers to the number of terms we include in the basis expansion of our block orbitals, while the meshing of the k-space basically refers to the meshing of the reciprocal space of the first Brillouin zone. These two quantities describe the numerical precision of our DFT calculations. Here I am showing how the energy per atom in a system I'm modeling with DFT changes with the value of the E-cut as well as k-point sampling in a plane wave self-consistent field calculation, and how we can choose these values of the energy cutoff and k-points via convergence study. Now I would like to point out why the band gaps in electronic band structures are underestimated using DFT. This is basically due to the so-called self-interaction errors, which are general to any effective field theory, not just DFT. Anytime you have an effective potential that's built from the total system, you are going to have self-interaction errors. Recall, in DFT we do not solve this many-body equation. However, we solve the one-body equation here, in which the interactions are functions of the density. Because the interaction in this Hamiltonian indicated by small h here basically built on the entire charge density, this leads that the orbitals will feel their own contribution to the interaction of the total potential. This means that an orbital would interact with itself. This leads to the so-called self-interaction error, which is an artificial effect of the mean field approximation. That means that the energy of an orbital would be a function of its occupation. Therefore, in general, in DFT, electrons tend to be unstable. They are destabilized compared to the actual situation, meaning that it is too easy to excite an electron by photon interaction, which leads to band gaps that are lower than their experimental counterparts. To give you a bit more quantitative picture, let's take a look at the energy of the system as a function of electrons in the system. If you have a quantum system and look at the energy of a system as a function of a number of electrons, you will have a piecewise linear function as indicated by this gray curve shown here. The reason for this is that because whenever you encounter a system with a fractional number of electrons, this system is in fact a combination. We call it a pure admixture of states with integer number of electrons. This means that if you are in a state between two integer electron number, the energy of that state is going to be the linear combinations of the two states that make the admixture. I would like to emphasize here that non-integer electron number do not exist intrinsically, but can exist if you do this linear combination of pure states. Now let's take a look at the DFT or the LDA solution presented by this black curve here, and you would notice that you are getting a convex hull in your energy. This convex hull behavior is basically because of the self-interaction errors, and this has a lot of consequences. To express this mathematically, the fact that this gray curve is linear can be written as the piecewise linearity condition here, which just states that the second derivative of the energy of an orbital with respect to its occupation equals to 0. Now, by taking the first derivative of the energy with respect to the orbital occupation, this is basically the chemical potential of the electron, or just the energy of the orbital, or the energy cost of occupying that specific orbital, so to speak. For instance, if you occupy this orbital by 10% of electron, you would just take this number here, which is the energy of that orbital, and multiply it by 10%, and this will tell you how much energy you are going to use. Combining these two equations here, you would get the so-called Koopman's condition. This Koopman condition basically states that the energy of the orbital should not change as a function of the orbital occupation, which means that the occupation of an orbital should not be the cause of the change of its own energy. This is called the self-interaction free condition. If an orbital self-interacts, when you occupy the orbital, its energy is going to change, means that the orbital modifies its own environment, which is unphysical, but unfortunately unavoidable in the DFT mean field approximation. Now, how is this connected to the band gap problem? If the function of the energy is convex due to the self-interaction, we are getting the first derivative of the energy of the orbital with respect to the orbital occupation to be larger than 0. This means that as you occupy an orbital, its energy is going to increase. Therefore, if you take or if you look at orbitals that are completely filled, namely the valence electrons, this means that its energy will be overestimated in the DFT simulations because as you occupy an orbital, the energy is too large. And the same thing goes for the conduction electrons as well. Because the orbital is unoccupied, the energy is going to be underestimated. Because of that, the band gap you obtain in the DFT simulations is going to be lower than their experimental values. To rephrase, let's take a look at the relationship between the energy and the number of electrons. Let's take a look again at this relationship. Here, if we have, you'll notice that the only position where the first derivative or the slope of the tangent of this convex hull is equal to the slope of this piecewise linear part is basically when the orbital is half occupied. This means that if the orbital is unoccupied, such as the case of the conduction band, this means that this first derivative here is too negative compared to the half-occupied derivative, which implies that the energy of the conduction band would be underestimated in the DFT calculations. And the same goes for the case of the fully occupied orbital, in which the slope of the tangent here is merely 0, or something that is larger than the slope of the half-occupied orbital, which implies that the energy of the valence or the occupied bands would be overestimated in the DFT calculations. So you can directly read the band gap by looking at the relationship between the energy as a function of the number of electrons. So in order to correct the self-interaction error, we perform the so-called Hubbard correction, or the DFT+U approach, just by adding these piecewise parabolas, which account for the energy difference between the DFT convex hull and the real piecewise linear function. Now, just to give a qualitative idea about what happens upon applying the DFT+U correction in the calculations and its practical implications in modeling the electron transfer and light absorption, I am taking here the case of barium titanate, which is a ferroelectric material, as an example. Here are the band structure of the BTO. On the left is shown using the ordinary DFT approach, and on the right is shown the band gap results using the DFT+U approach. And you would notice that the Hubbard correction basically corrects the underestimated band gap here, and the resulted value is something like 3.4 electron volts, which matches the experimental values. Now, concerning the optical properties, let's take a look at the dielectric function, or the DFT calculation of the dielectric function of the same material, BTO as well. And you can find here at the bottom the quantum mechanical expression of the dielectric function expressed in the momentum space. And you would notice that how the values of the dielectric function depends on the band gap values, or the difference in energies, or the transition energies between levels. Basically, this band gap affects the onset of the imaginary part of the dielectric function, as shown here, as well as the value of the dielectric constant at 0 frequency, as shown here from the real part. And it's obvious that the DFT underestimates the value of the band gap compared to the DFT+U approach, which gives the value that's comparable to the experimental measurements. This, of course, is directly relevant to the optical properties, like the refractive index and the absorption coefficients. Taken into account that these optical properties basically depend on the real and imaginary parts of the dielectric function, as shown here. Here are the values of the BTO, the values of the refractive index, as well as the extinction or the absorption coefficient, evaluated using the DFT+U, or the Hubbard correction. By this, I hope I had given you just a brief idea on why the DFT calculations underestimates band gap, and a short qualitative idea on Hubbard correction, and what are the practical implications in modeling electron transfer and light absorption properties if you perform these Hubbard correction. Thank you so much for your attention.